Welcome back to our video series about RC circuits. And what we're going to do in this video is we are going to have another look at the analysis, but go through it in a more systematic way. A way that you are probably going to use from now on when you are looking at these circuits. But before we do this, let's actually look at, well, do we only know how to analyze circuits with one resistor, one capacitor, and a voltage source? Well, no, I can actually analyze circuits that are a lot more general. In this case, we are looking at a system with still one capacitor, but I could have multiple sources and multiple resistors. Well, one thing we know is capacitors are linear, resistors are linear. This is actually a linear system. For linear systems, I can use superposition. So I can look at the effect of each source individually. So when you analyze these circuits, this is typically what you want to do. Now, what I also can do is in linear systems is I can replace everything that is connected to the capacitor by its Thevenin equivalent. So I can replace all these resistors and the voltage source by their Thevenin equivalent. So I can find the equivalent system that basically just has one resistor, one capacitor, and one source. And I am back to the system I have analyzed. So even though we are only looking at the simple system with one resistor, one capacitor, and one voltage source, it actually covers a whole wide range of these very similar systems through superposition and a Thevenin equivalent. So it makes sense to spend so much time on analyzing just these simple systems. Okay, so suppose I would give you this RC system, and I say, well, my source Vs varies in time as shown here. Analyze this. Well, you typically are going to use 3 steps. The first step, you're going to evaluate what is the situation just before the event happened. Okay, just before the event, what do I know? Well, I assume everything has settled. It has been a long time. The voltage Vs has been equal to V0 for a long time. So everything has settled. When there are no changes in time, I know the capacitor behaves as an open circuit. So just before the event, this is what my circuit actually looks like. And this is simple to analyze. All the currents are equal to 0. The voltage over the resistor is equal to 0. And the voltage over my capacitor is equal to this V0. So this is what I know the situation is just before the event. Then the second step, I'm going to consider what happens during the event. So what happens is that right after the event, what do I know? Well, a lot of things can change in my circuit. A lot of things can vary, but there's one thing that cannot. It is the capacitor voltage. So the voltage over the capacitor cannot change instantaneously. And this is what relates what the situation is before my switch closes and after it closes. It's only the capacitor voltage. So I know the capacitor voltage has to be the same. What happens to the resistor voltage? Well, that can change, but I can calculate that because I know the capacitor voltage. So now I have a different system that I can analyze. I know Vs because Vs has just switched to V1. I know this voltage, and that's enough for me to calculate everything else. I can calculate what's the voltage drop over my resistor. I can calculate what is the current through my resistor. So, and I see that indeed the resistor voltage does jump. Okay, so this is right after the event. Then the third step is, well, how does it go from there? And to answer that, let's look at what is the situation after a really long time. So let's look at what happens after a time when everything has settled. So when everything has settled, again, nothing is changing anymore. When everything has settled, the capacitor behaves as an open circuit. So I again have this system that I can easily analyze. All my currents are equal to 0. The voltage drop over my resistor is equal to 0 as a result because of Ohm's law. And again, my entire voltage V1 is now across my capacitor. And so I know that after a long time, this is where my capacitor voltage is going to end up, and this is where my resistor voltage is going to end up. Okay, and what happens in between? Well, I know because I have one capacitor, this is going to be a system that can be characterized as a differential equation of the first order. And I know that for these systems, the solution is an exponential function. So I know that in between, I'm going to have an exponential function, and I'm just going to write this exponential function. Let's start with VR. Right? So I'm writing this exponential function, and I have two unknowns, a and b. I also know that this is going to be a decaying exponential with this time constant RC. So this is really the only thing you have to remember. It is going to be a decaying exponential with this time constant tau. A and b I don't know. But what I do know is that this exponential starts here and it ends here. So I have these 2 points, and I can just evaluate it, and from that I can find a and b. So this is the expression of my resistor current, my full mathematical expression. So I don't actually have to go to the differential equations to solve it. I can do the same for capacitor voltage. It is also going to be an exponential. I again going to say, well, I have these two unknowns, a and b. I know it's going to be the same time constant RC. I know where the voltage is going to start, where it is going to end. So I have these 2 points. I can solve for a and b, and I can find the entire expression. So this methodology is really the way in which you can quickly solve these kind of circuits. And this is just a very general way in which you can solve these circuits, and which is also an easy way to remember how to do it. And that is basically a good methodology on how to solve RC circuits.